if I have a shaft, and let's say there is a rotor on the shaft, and then for some reason, just let's assume that the CAG of the rotor is slightly eccentric to the shaft. So it's displaced from the center line of the shaft. Well, with the mass of the rotor, or the weight of the rotor, the shaft is going to deflect. So you can imagine this supported at this point here. Let's say the shaft is supported here and here. What we have is a weight acting down on it, and that's going to make the shaft deflect like this. There's a bending moment on that shaft. So when it deflects, the shaft, now the center axis of the shaft goes like this, and we have this deflection D. So we have a shaft, and then we are going to provide a torque, and it's going to start spinning. When it starts to rotate, there will be a centrifugal force, and that force is going to get the shaft to deflect even further. So it's going to go to this position. So if you remember, the shaft was something like that. It is now, due to centrifugal force, deflected down to this position. The centrifugal force acts through the CAG, so it's acting from this distance here, and that distance there is E, the eccentricity of the rotor. So we can say that the centrifugal force is m omega squared, and it's obvious by the radius, but in this case it's going to be y plus this value E here. So that's the centrifugal force on the rotor and on the shaft. Fair enough. Then, if we had the shaft, it's acting a bit like a spring, and maybe just consider, shaft here, we apply a weight to it and it deflects down to here. When we take that weight off of it, it'll spring back up into this position. So it has some springiness, K. And when I like any spring, if we had a spring here, if we stretch it down to this value y and we let go, there'll be a force forcing it to go back up. If I stretch it down here a bit further, that force will be bigger and it'll shoot back up faster. So the force acting in this direction is the springiness of the shaft by its deflection y, how far we deflected. So we can say, when it's in equilibrium, that the centrifugal forces must be equal to these stiffness forces. So there's that equation, and I'm going to just multiply it out. So we get m omega squared y and m omega squared e. We're going to bring the y's to one side, so we get m omega squared e is equal to ky minus m omega squared y. Take the y out of it, and then divide both sides by k minus m omega squared. Then we'll clean it up by dividing above and below the line by m omega squared, and we get this expression here. Okay, so what's to be observed here is what happens when that value is equal to 1. So when that becomes equal to 1, this entire expression becomes e over 1 minus 1. Now 1 minus 1 is 0, and anything divided by 0 is infinite. So we're saying y becomes infinite, and that is when the whirl or the shaft is said to whirl. So what that means is, you could see the shaft vibrating up and down like that. So we want to stay away from this speed, okay? And we're going to call this the critical speed, omega c. So when this expression is equal to 1, we're at this critical speed. Okay, so there it is. We've called it the critical speed, and just rearranging that equation, we have the critical speed squared is equal to k over m, or omega c is equal to root k over m. So I'm just going to park that equation for a minute and put it over here. Now, going back to the spring, we see if we have, a weight attached to the shaft, it'll want to pull it back down. But when it's in equilibrium, that weight is going to be equal to the force that's trying to bring it back up again, which is the springiness times the deflection. Okay, so this is deflection d, the static deflection d. So if it's in equilibrium statically, okay, so it's not turning it at this stage, it's just a static shaft, then we can say that kd is equal to mg. Okay, that's from this guy over here. We can rearrange that to say that g over d is equal to k over m. But k over m is equal to omega c squared. So omega c squared is equal to k over m, which is g over d. So that's the critical speed, okay, in radians per second is equal to g over d. If we want to get that in a time format or a time period, well, from a simple harmonic motion, the periodic time is 2 pi times the displacement over the acceleration. The displacement is this deflection d, and the acceleration is the acceleration due to gravity. Okay, so we've two formulae here what we can use. Sometimes we want to talk about the frequency, which will be in hertz, or it'll be revolutions per second. So frequency is just 1 over t, so it'll be 1 over this expression. So the frequency is 1 over 2 pi times square root of g over d. Now, if we look at this, the root of g, well, g is 9.81, so the square root of 9.81 is 3.132, and pi is 3.141. So if I divide root g by pi, I get 0.99 something. Okay, so we can say that's approximately equal to 1. So these cancel out. So we're left with the frequency, or the revolutions per second, is equal to 1 over 2 times the square root of d, and this is the static deflection. Okay, so that is the speed we want to keep the shaft away from. Okay, we don't want the shaft to rotate at that speed, or else it will whirl. When it's not whirling, okay, so at speeds other than the critical speed, the deflection of the shaft can be considered to be e over the critical speed squared minus whatever the speed is, minus 1. So just to reassure you though, if the shaft was to whirl, there will be some damping in the shaft, so it won't actually become infinite. But we should keep the shaft speed well away from the critical speed where we can. So that's an introduction to it, and it'll probably become, well, I hope it becomes more clear when we do a few examples.